Have you ever wondered why some materials conduct electricity effortlessly while others don't? What makes copper and aluminium good conductors while glass and rubber insulators? The answer lies deep within the atomic structure of solids in what we call the band theory. This theory explains the fundamental difference between conductors, insulators, and semiconductors. To understand band theory of solids, we first need to look inside an atom. We are familiar with the classical model of an atom where electrons revolve around the nucleus in specific orbits, whereas the quantum mechanical model describes orbitals as regions of space around the nucleus where there is a high probability of finding electrons. In both the models, each electron in an atom has a specific energy. This energy can be represented using an energy level diagram, where horizontal lines indicate discrete energy levels. The energy of an electron primarily depends on its distance from the nucleus. Further away from the nucleus, higher its energy. Therefore, electrons in different orbits within the same atom have different energies. Energy also depends on the nuclear charge. A higher positive charge on the nucleus exerts a stronger attractive force on electrons, lowering their energy. For example, the energy of an electron in the first orbit of a hydrogen atom is higher than that of an electron in the first orbit of a helium atom. The energy of an electron is also influenced by its interactions with other electrons. In short, we can say that the energy of an electron depends on the charge configuration with which it interacts. When the charge configuration around it changes, its energy changes. If we consider two atoms of the same element separated by a large distance such that there is no interaction between the two atoms, then the electrons in both atoms will have same energy levels. However, when these two atoms come close to form a molecule, the electrons in each atom interact with the charges in the neighboring atom. These interactions changes the energy levels of electrons, which may increase or decrease depending on nature of interaction. The outer electrons are more affected as they are closer to the neighboring atoms, while the inner electrons remain largely unaffected. When two atoms interact, each energy level splits into two slightly different levels. With three atoms, the same energy level splits into three levels. In a solid where there are millions of atoms packed together, these split levels become so numerous and closely spaced that it appears to be continuous. This continuous set of energy levels forms an energy band. Energy band in a solid can be fully occupied by electrons, partially filled, or completely empty. Let's understand with an example. Sodium has 11 electrons. These electrons are distributed among different orbitals, each corresponding to a specific energy level. Let's look at the electronic configuration of sodium atom. 2 electrons in 1s orbital, 2 electrons in 2s orbital, 6 electrons in 2p orbitals, and 1 electron in 3s orbital. An s orbital can hold a maximum of 2 electrons, and a p orbital can hold a maximum of 6 electrons. Therefore, 1s, 2s and 2p orbitals are completely filled, whereas 3s is half filled. 3p and other higher energy orbitals are completely empty. These energy levels split into bands in a sodium solid. 1s, 2s and 2p bands are full. 3s band is half filled and 3p band is empty. The highest band that is completely filled at absolute zero temperature is called the valence band. The band above the valence band is called the conduction band. Electrons in the conduction band are not bound to individual atoms. Instead, they are free to move throughout the material. This movement under an applied electric field results in electric current. The separation between the valence band and the conduction band is called the energy gap. At absolute zero temperature, there is no thermal energy available. But at higher temperatures, electrons can absorb thermal energy to jump from the valence band to the conduction band. This is called thermal excitation. Larger the band gap, the higher the energy needed for thermal excitation. In insulators, the conduction band is completely empty and the valence band is full. There exists a large band gap, typically greater than 3 electron volts, which requires very high temperatures, making thermal excitation impractical. Therefore, at normal temperatures, insulators do not conduct electricity. In semiconductors, the valence band is full and the conduction band is empty at absolute zero. However, due to their small band gap, typically less than 3 electron volts, some electrons can get excited to the conduction band even at room temperature. This allows semiconductors to partially conduct electricity. A conductor has a large number of electrons in the conduction band even at absolute zero temperature. Therefore, resistance of such materials is low or conductivity is high. The presence of large number of electrons in the conduction band could be because of one of the two reasons. 1. Overlap of the conduction band and the valence band. In metals like zinc, there is a partial overlap of conduction band and the valence band. Due to this, there is no energy gap. When an electric field is applied, these electrons readily move, creating an electric current. 2. Partially filled conduction band. Even at absolute zero temperature, the conduction band can be partially full, as we saw in the case of sodium. This allows free movement of electrons, making conduction possible in such materials. And that's how the band theory explains the electrical properties of solids. Thanks for watching.